Good morning, dear student, and welcome to our very first Microsoft Team lecture. So today we are going to do an overall presentation of the Lebesgue theory and its application. So in order to introduce the Lebesgue theory, we need to talk about Riemann integral because it is the difficulties or the weakness of the Riemann integral to solve some integration problem that led Lebesgue to set up or to invent the theory of measure theory. So the Riemann integral is a simple procedure which in real analysis allows to determine or to define the integral of the function over an interval. This can be interpreted geometrically as the area of the domain under the representative curve of the function f. It can also be used to define the length of a rectifiable curve of the plane or space. The procedure used to define the Riemann integral of a function f consists of approaching it by simple functions over partition of the interval on which the function is defined in such a way that the area under the curve is easy to compute. Function for which this definition makes sense are said to be Riemann integrable. This is typically the case of function, of continuous function, piecewise continuous function, monotonic, or more generally, a regulated function on the closed interval AB, where the function is defined. So for such a function f defined on the closed interval AB to R, we can define the Riemann integral to be the limit of the Riemann sum. And the Riemann sum is defined to be this finite sum where j runs from 0 to n, f of psi j into delta x of j. So we take the limit of this finite sum. If it converges, it will converge towards the definite integral of the function. So in the above definition, x sub j is defined to be the lower limit of integration, that is a plus j into the space delta x sub j. That is the grid space. And in this case, j is in the range of 0 up to n minus 1. And psi j is in the interval x sub j plus 1. And delta x sub j is the difference between two consecutive points, x sub j plus 1 minus x sub j. And this actually gives us delta x, which is defined to be b minus a divided by n, the number of subintervals. So the Riemann integral also allows to define the length of some subset of R which are not interval. So if we take, for instance, a subset of the interval AB, which we denote by E, the bounded subset, we say that E, the subset of AB, is a Riemann measurable set. It's a Riemann measurable set if it indicates a function or its characteristic function, one sub E is Riemann integrable over the interval AB, and we denote it by LE, the integral from A to B of the indicator function of E dx. So this will represent the length of the set E. So the theory of the Riemann integral extends naturally to non-bounded function defined on bounded or unbounded interval. Even though this theory has been very useful in mathematics and has had numerous applications in various domains, among which we name physics, it turns out that it is insufficient to address some problems in infinite dimensional spaces, which are the subject of function analysis and in probability theory. In fact, on one hand, regularity conditions imposed to function are too restrictive. And on the other hand, resulting computational techniques are difficult to use due to the fact that taking the limit under the integral sign requires, in general, a uniform convergence. So if you take for an example, the Dirichlet function, chi, which is by definition the indicator function of the set of rational number intersection with the closed interval 0, 1. And at each x in the interval 0, 1, the value of the Dirichlet function will be 1 if that x is a rational number and 0 if it is irrational. So this Dirichlet function is not Riemann integrable. So in other words, the countable set Q intersection closed interval 0, 1 is not Riemann measurable, whereas we shall see later on that it is Lebesgue measurable with a null measure. Indeed, since Q, the set of rational numbers, is countable, it is a countable union of singletons, and the length of a singleton of R is B0. It is natural to consider that the length of Q is 0 by the countable additivity of length. It therefore becomes essential to extend the class of measurable sets, and by the same token, that of integrable function, while having easier to use calculation techniques. There are several ways to achieve this goal. It is Henri Lebesgue who finally succeeded to achieve that goal by introducing a new integral that bears his name, the Lebesgue integral. The idea is to start by measuring the length, respectively the area, the volume, of a reasonable class of subsets of the number line, respectively plane space, which we should call measurable sets. Then define from there measurable function and the integral of a non-negative measurable functions, starting from the analogous of equation 1 for measurable sets. In order to give a first idea of Lebesgue's procedure and compare it to Riemann's, let's consider the simplest case where f is a non-negative function defined on an interval t that is contained in the number line R, and whose range is in the closed interval 0, 1. While a Riemann integral is defined by partitioning I, that is the integral, the limit of integration, or the set over which we integrate the function, in small subintervals, and by approximating f by associated simple function. The Lebesgue integral, on the other hand, is defined by partitioning the destination interval 0, 1 in n, in capital N small subintervals y sub k minus 1, comma, y sub k of size delta x sub k, which is given by k by n, where k takes the value from 1 to n. So for this one, we refer to figure 1, which we should display very soon. And by approaching the function f by simple function phi n, which will be piecewise constant function defined by phi sub n of x is equal to y sub k if x is in ek. And what is ek? Ek is defined to be the set of x in the interval I, where f of x is in between y sub k minus 1 and y sub k. And this set ek is also denoted by a sub nk. And k takes the value 0 up to capital N being the number of subintervals. So En, because we define Enk and the final, we define above, we define Ek here, okay, taking the value from 1 to n. Now, finally, we also define En, which will be ANN, is just the set of element of I such that f of x is greater or equal to 1. So this is our figure 1 that I indicated above. And we are partitioning the destination set, and y1 is the smaller value taken by the function here, and then we have x2, x up to, yk, yn minus 2, yn, y sub n minus 1, and so forth. So these are the various points of the partition of the destination set or the range of the function. And along the x-axis, we have our interval AB, which we don't partition, but what we do, we take the pre-image of each of these subinterval, yk minus 1 yk, right? And then we take the reciprocal. The reciprocal will give us a set E sub k, which can be union of subintervals of the real number, as you can see here. So it is natural to define the integral of f as integral along I of f of x d lambda x equal by definition. So that's how we define it. We take the limit when capital N goes to infinity of the sum of y sub k lambda ek, where k runs from 0 to n. So the ek's have been defined above. Yk is the value taken by the function f. For obviously x in E sub k. So I think it's better to, so this is our ek here. You can see that f of x is in this interval, yk minus 1, yk. So if x is in ek, the range of x will be, or the interval, the range of x for an element in ek will be y sub k minus 1 up to yk. So this is how we define the integral of f. And this definition is different from the definition of the Riemann integral, because here we first partition the destination set or the range of f. And by the pre-image, we will be able to define the E sub keys. And this will allow us to take the limit and define what the integral of the function is. So the definition of the integral as we gave in the previous slide will make sense provided that the lambda EK are well defined, which is precisely the hypothesis of measurability that must be imposed on the function f. So the collection of phi sub n, where n is an element of the natural set, the set of natural number, this collection will form a sequence of non-decreasing simple function that converges pointwise to f. The additivity of the length measure allows to easily deduce the formula of the area under the curve. And we have the definition, which is given by the following formula given by equation 2. And in this formula given by equation 2, mu sub f is defined to be equal to lambda, that is the measure of the set of f greater than or equal to y. So this definition. So we would denote lambda of the set of f greater than or equal to y as mu sub f of y. And this one is the Lebesgue length measure of the measurable set f greater than or equal to 1, which we can see rewrite as the set of x in I such that f of x is greater than or equal to 1. And the integral on the right-hand side of equation 2 is the Riemann integral of the monotonic, non-increasing, non-negative, and bounded function mu sub f defined at x. We associate lambda of the set of f greater than or equal to y, and 0 for x strictly greater than 1. So in other words, the Lebesgue integral is defined by approximating the function f by simple functions associated with partition of the destination interval, the one containing the range of f. We shall see how this different approach leads to a more general theory and much more simple. So to come back to the foundation of measure theory, Lebesgue's problem can be stated as follows. Find the class L, which is a subset of the power set of R, containing intervals of R and having good properties of closure under completion, under complementation and countable union, and a set of functions lambda defined from L into R plus bar, which is an extension of the real line. So it should satisfy the various conditions. So this set of function lambda should satisfy the following properties. So the first property that lambda should satisfy is that lambda of the closed interval AB should be equal to B minus A, which is actually the length of the interval, the closed interval AB. And this should be for any interval I equal to the closed interval AB. So the second property that this set of function lambda should satisfy is that lambda should be sigma additive over calligraphic L, which means that if we take a sequence of sets or a sequence of AN of element of L pairwise disjoint, then if you take the union of such set and we denote that union by A, it should also be an element of L, and beside lambda A should be equal to the sum of all the lambda AN. So this property is denoted by additivity property of lambda. And the third property that lambda should satisfy is that lambda should be invariant by translation. That is, for any A in calligraphic L and for any element of R denoted here by B, if we define A plus B to be the set of A plus B, where A is in the set capital A, this sum A plus B should be in L, or calligraphic L, and the invariance by translation property of lambda should be that lambda A plus B should be equal to lambda A. So meaning that if we add B to A, it does not change the value of the measure of A. It remains invariant by translation. So A plus B is what we call the translation of A by B. So in 1905, Giuseppe Vitali used the axiom of choice, which is an axiom from algebra. Axiom, it's a set theory axiom, actually. So he used the axiom of choice to prove that there is no set function that is sigma additive over the entire class of the power set of R, and satisfying the above properties, which we would denote to be the property of a measure function. Okay, so we should see how Lebesgue solved this problem by showing that there exists a reasonable class, calligraphic L, subset of the power set of R, and a unique set of function lambda defined from calligraphic L into R plus bar, satisfying those properties. This is what we call the Lebesgue measure on R. The measure on R is exactly such a lambda that satisfies these three axioms or properties. Then we shall briefly present the general measure theory following a method slightly different but largely inspired by Lebesgue. This method, called category extension method, allows one to construct a general theory of measure that is applicable to other situations encountered in function analysis and probability theory. It is in this general framework that we will introduce the notion of the Lebesgue integral with respect to a measure, and we will state essential results pertaining to the Lebesgue integration theory. The ideas used in the construction of Lebesgue measure on the number line are the following. First of all, we want the measure lambda of an open interval to be the length of the interval. Since every open subset O of the number line is a countable union of disjoint open intervals. That is, O can be written as a countable union of interval of the form AKBK, where the interval AKBK denoted by I sub k are pairwise disjoint. And for that, we must have that lambda of O, open interval, open set O, the lambda of O written in this form will be the series of the differences of bk minus ak. So for an arbitrary subset E of R, which is not necessarily an open interval, we will denote lambda E to be the infimum of lambda O's, where O is an open set and E contained in O. Yeah, I think that this G is actually O. Wait, no, I don't think so. Okay, so this G actually, because this infimum will be taken on O, right? So this G actually should be a collection of O, right? Yeah. So what are we doing? We take all possible covering of E, that is, we take E in the union of O like this, where O are open interval, and we take the infimum on such O. So for a given E, arbitrary subset of R, we can always cover E by infinitely many open intervals. So if you have a covering of E by open interval, we compute lambda of each of these O covering E, and we take the infimum on all the possible O that will cover E. So that's how we should understand the definition of lambda E. So the difficulty with this is that lambda is not a measure on the sigma algebra PR. So that is the difficulty. Because it's not a measure on PR, it means that we are not sure that for an arbitrary E in R, we'll be able to define lambda E. So in other words, we need to find a sigma algebra lesser than PR, over which this definition will make sense. So to resolve this by considering a strictly smaller sigma algebra, right? That's how we should resolve the problem. We consider a strictly smaller sigma algebra where lambda E will make sense, right? That is where this lambda will be a measure, because we need lambda to be a measure over a sigma algebra. But as we saw with the result obtained by Vitali in 1905, we saw that there's no measure, so there's no measure over PR. So that's the reason why we need to find a strictly smaller sigma algebra on which lambda will be a measure. We need to find a strictly smaller sigma algebra over which lambda will be a measure. So this is essential. This is the essential idea behind the construction of Lebesgue measure. But it is technically simpler to work with interval of the form AB, where the interval is open at A and closed at B, rather than open interval. So, first definition, we define what is an outer measure. So capital X here denotes a non-empty set. So we will define mu star a mapping from the power set of X into the interval, the closed interval 0 to infinity, meaning that it contains infinity. So mu star can take the value infinity. So such mu star is called an outer measure if it satisfies the following three axioms. So first axiom is that mu star of the empty set should be 0. If A is contained in B, or if A is a subset of B, then mu star of A is less than or equal to mu star of B. And the last axiom, which we call subadditivity, is that if we have a sequence of subset of capital X, that is A1, A2 up to infinity, that is, we take a sequence of such sets, mu star of the union, or the countable union of all the AKs, should be less than or equal to the series of mu star AK, where K runs from 1 to infinity. So that's the definition of an outer measure. So a set N, or calligraphic N, is a null set with respect to the outer measure mu star if mu star of N is 0. So a common way of generating outer measure is as follows. So first of all, we consider a collection C, subset of the power set of X, with the property that the empty set is an element of that collection C, and there exists a sequence in C, D1, D2 to up to infinity, such that X is a countable union of D sub K, where K runs from 1 to infinity. So if we consider such a collection, we can now define mu star of E via a certain function L, defined from C to the interval 0 infinity. And we assume that L of the empty set is 0. And we are going to define mu star of E to be the infimum of the series of L of A sub I, where I runs from 1 to infinity, and each A sub I is an element of the collection C for any I, and E is contained in the countable union of the A sub I. So in other words, the A sub I is form what we call a covering of E. So if we construct mu star in this fashion, that is using equation 3, therefore mu star is an outer measure. So this is a way to construct an outer measure, and this result is a proposition. So as an example, if we take capital X to be R, and we let C, the collection, or we let C to be the collection of interval of the form AB, where it is open at A and closed at B. And in our case, our L I will be b minus a, meaning that actually Li will measure the length of the interval I, where I is the interval open at A and close at B. So we define mu star by equation 3 of the proposition, which is proposition 2.2. No, sorry. Equation E is this proposition. It's not, there's no name. It's not number. So proposition 2.2 below, because that's what we are going to define later on. So proposition 2.2 oh, sorry, I think I'm mistaken. Since I don't see the numbering here, but proposition 2.2 is actually this one where we define equation 3, right? So if you define mu star in our case, because we are trying to adopt, right? Because in the proposition, we just assume that such a function L exists, but now we are actually defining L to be the length of the interval I. Since we know that what L is, so we can use that in the case of R to define our mu star, right? So from this proposition, we know already that such a mu star will be an outer measure. But we will see later that mu star is not a measure on PR. It's an outer measure. That's why we call it outer measure. But however, if we restrict mu star to a sigma algebra L, calligraphic L, which is strictly smaller than the power set of R, then mu star will be a measure on calligraphic L. So that restriction which becomes a measure is what we'll call the Lebesgue measure, and we did not that measure by lambda. So in other words, what we are saying here is that what we denote by lambda will be the restriction of mu star over calligraphic L. Because mu star itself is not a measure, it's an outer measure, but if you restrict it to calligraphic L, which is a sigma algebra, that restriction will be a measure which we denote or we call a Lebesgue measure. So we are going to construct a sigma algebra from the definition of, from an outer measure. We are going to see how we can define a sigma algebra, knowing that the restriction of mu star on that sigma algebra will give us a measure. So definition. So we let mu star to be an outer measure and a subset of capital X, right? Such a set is called or is termed or is said to be mu star measurable if mu star of E is equal to mu star of E intersection A plus mu star of E intersection A complement, and this should be true for any subset E of capital X. So a set A, subset of R of capital X, will be mu star integrable if it satisfies the condition given by equation 4. So characteristics theorem tells us that if you take the collection of mu star measurable set, it is a sigma algebra. So in other words, what characteristic theorem is telling us is that if we define our calligraphic A, that's a definition, to be the set of E, or a set of A of that form, A subset of X, such that A is mu star measurable. So this set is a sigma algebra. So that is what Karateodori theorem tells us. We have already a sigma algebra. And now if you take the restriction of mu star, that is the outer measure, we take the restriction on A, this gives us a measure which we denote by mu. So it's by the same token that we define the Lebesgue integral, the Lebesgue measure, as mentioned above. And moreover, this sigma algebra, calligraphic A, contains all null sets. Remember how we define null sets? We say that a set is called a null set if mu star of that set is 0. So if its its outer measure is 0, we call it null set. Okay, now if we let capital X to be a non-empty set, we can define an algebra, right? So a collection of subset of capital X denoted by calligraphic A, subset of the power set of X, is called an algebra if the following conditions are satisfied. First of all, that collection, calligraphic A, should contain the empty set. And now, if capital A is in the collection calligraphic X, then its complement is also in calligraphic A. And the third property or axiom is that if we have a finite element of calligraphic A, that is A1 up to AN, finite number of element of the collection A, then the finite union of AK, where K runs from 1 to N, is still in A, still in calligraphic A. Right. So a collection that satisfies these three axioms is called an algebra. Now, if I have an algebra, and if besides A being an algebra, it satisfies the fourth condition, we will call it a sigma algebra. So what is the fourth condition that an algebra should satisfy to be called a sigma algebra? Is that if not take not a finite number of element of A, but if you take a series of element of A, the countable union of the element of that series is still in A. So actually, there's a missing, here we have a key, right? So we should have a key here. So actually, this is what we should have, union AK, where K runs from 1 to infinity. This should be in A. So this is a definition of a sigma algebra. So a sigma algebra is an algebra, meaning that a collection that satisfies these three axioms. So an algebra that satisfies the fourth property, that is stability by countable union of element of the set, or stability by countable union of element of that set. So if X is a non-empty set and A is a sigma algebra, the pair XA is called a measurable space. And any element of that sigma algebra is called a measurable set. Or we can say that the set is immeasurable. So as an example, we can give like you can see on the slide, we have two examples here. The first example, if we take our non-empty set X to be the closed interval 0, 1, and if we let calligraphic A to be the collection of the empty set, capital X itself, that is the closed interval 0, 1, and the following two subintervals, the following two intervals, the closed interval 0, 1/2, and the interval open at 1/2 and close at 1. So this collection A of subsets of X is a sigma algebra, meaning that it satisfies the four axioms given in the above definition, 1, 2, 3, and 4. The second example, if we take our capital X to be the set made of three elements, 1, 2, 3, and if we construct a collection of subset of capital X made of these four elements, the empty set, capital X itself, the singleton one, and the pair, not the pair, but the pair 2, 3. Then A is a sigma algebra. So I think let's quickly check that is a sigma algebra, particularly the second case. You can focus on that. So is the first condition satisfied? Yes. For the first condition, or the first axiom, we see that we have the empty set here in the list of the collection. So the empty set is an element of our collection calligraphic A. So that's for the first axiom. So the second axiom, we are going to take each element of calligraphic A here and see if the complement is still in A. In other words, we can summarize axiom 2 to say that A is closed by complementation. Closed, or it's stable by complementation. Now, let's take the first element, the empty set, right? So if I take A to be the empty set, so if I take my A to be the empty set, I compute the complement of the empty set. This is X. Is X in A? Yes, X is in A. So this is in A, right? Obviously, this is an element of A, right? The empty set. So I take another element of A, which is X itself, right? So if I take X itself, I don't need to do that because this, the fact that the complement of the complement is A itself. So if I take the complement of X, it will give me A, which is the empty set. But we can still write it. Sorry. So the complement of X is the empty set. And we know that the empty set is and this is actually a complement. And if you do the same thing here with the singleton one, so the singleton one, if you take the singleton one, its complement will be the pair 2, 3, and this is in A. And now if you take the pair 2, 3, its complement is 1. Of course, when you say complement, it's complement with respect to X, right? And this also is in A. So we can see that axiom 2 is satisfied. And we prove it by taking each point of calligraphic A as given. So we are going to look at the next axiom, axiom 3. So for axiom 3, okay, for axiom 3, we can take arbitrary. You can take arbitrary element, provided we have a finite number of element of A. We can select them arbitrarily. So, finite number of them. So if we take, for instance, 2 elements, that is, if we take 2 elements, because to construct a union, we need at least 2 elements. Now, if you take A1 and A2, that is, we assume that n is equal to 2, 2 element first. I can take any of these. So my A1 can be any of them. A1 can be, for instance, the empty set, and A2 can be X. Now, if I take the union of the two, it's still X, and we know that this is in A. All right. So I can take any combination, any possible combination. Right? So I can take A1 equal to 1, the singleton 1, and A2 to be the pair 2, 3. Now, if I take the union, A1 union A2, this is X, and X is in A. I can take the empty set and 1. If I take the union, it's the singleton 1, which is there. I can take 1, the singleton 1, and X. I can take X and the pair 2, 3. So any possible combination will still give us, the union will still give us an element of A. Now, I can take n equal to 3 and take the combination of 3 consecutive or 3 possible elements here, the union will still be inside. Now, if I take 4 element 1, 2, 3, 4, this is A1, A2, A3, A4, and they take the union of all these elements, it will give us X, which is still there. So you see that if I take a finite union of arbitrary element of A, it will still be there. So what we have just done will be exactly the same if we were taking a countable union. Countable union, meaning that we take a sequence. Because A, the collection A, has a finite number of elements. That is, the cardinality, the number of elements of the collection, is finite and is equal, in our case, is equal to 4. Because of that, if you want to construct a sequence of elements of that, we cannot have infinitely many different elements in that sequence. So it means that there are terms in the sequence that will repeat. In other words, what I'm saying is that we can take, for countable union, so if you take a sequence like this, AK, sequence of subset of A. Sequence means that K here, we have infinitely many. So because A is finite, finite element. And now from this sequence, what we can do, we can take, for instance, A1 to be the empty set, A2 to be X, A3, the singleton one, A4, the pair 2, 3, sorry. And now, for any n, or for any k greater than or equal to 5, we can set all this ak to a fixed value. It can be either, it can be any of these 4 elements, because they will have to repeat. We can decide that it's the empty set, or it is the set X itself, or it can be the singleton one, or it can be the pair 2, 3. So it can be either any of them. So to simplify, we can set all this to be the empty set. And with this, we are back to the case of finite union here. Because when we take the union of all these elements, it will be similar to what we did already. So in all the cases, if you take the union of all these elements, it will still give us, actually, it will give us X. In this case, the union would give us X. Right. So this is just a construction. We can construct it in many ways, right? We can even exclude X from our sequence because it's an arbitrary sequence. So we can construct our sequence in which none of the AK will be X. Still, because this element, the union, will give us X. Because if already these two are in the union, when we take the union, it will give us X. Still, if we exclude even these two, X and the singleton one, and we just take the empty set and the interval, and the pair 2, 3, meaning that if our sequence will consist on only these two terms, or these two sets, the union will still give us the pair 2, 3, which is still an element of the collection. So anyhow, if you take all possible combinations to define our sequence of subset of calligraphic A, we have definitely a sigma algebra. Okay, so that is for the example. Now, if we have a collection C of subset of X, we can define sigma C to be the intersection of all the A sub alpha, where A sub alpha is a sigma algebra that contains C. So sigma C is a sigma algebra. And it is what we call the sigma algebra generated by C. If capital X has some additional structure, a structure of a metric space, for instance, or a topology. A metric space is a topology. We saw that. Then we talk about open sets. When we have a metric space or a topology, we can talk about open sets. Now, if we denote by calligraphic G the collection of open sets of X, then the sigma algebra generated by G or calligraphic G will be denoted by B or calligraphic B. And such a sigma algebra generated by a topology is called the Borel sigma algebra of X. We have a proposition here. If we take X to be a real number R, then the Borel sigma algebra B is generated by each of the following collection of sets, right? So B is a Borel sigma algebra defined here, right? We say that is the sigma algebra generated by the topology of X, because we take a collection of open sets of X. Now, we take the particular case where X is R, and we still consider that B, that Borel sigma algebra generated by the open set of R. So we are saying that this same sigma algebra B can be generated by C1, C2, C3, C4. It will give us the same result. So in other words, we are saying that B can also be the sigma algebra generated by C1, and it's the same if we take it to be generated by C2 or generated by C3 or generated by C4. So in other words, if you want to work with the sigma algebra, the Borel sigma algebra of R, Borel sigma algebra of R, we have the choice between using this definition or using this definition or this or that and that. So the choice is ours. We can work with any of this collection and say that the Borel sigma algebra over R is a sigma algebra generated by any such collection. That it can be the collection of open interval of the form AB. It can be a collection of closed interval AB. It can be the collection of interval of the form open at A, close at B, or it can be collection of the interval open at A and open at infinity. So all these four collections define the same Borel sigma algebra B. And it's also sometimes we also define B or denote B as BR. So if you see BR like this, it's exactly the same. So sometimes it's denoted by BR. So I think that I will make a pause after this one. So we'll go through a few slides again, and then there will be a pause, and we'll continue after. So now we are going to define a measure. So a measure, we define a measure when we have a measurable space, which we defined previously. So that is a measurable space is just a pair of a non-empty set and a sigma algebra over that non-empty set. In our case, we take X, the pair XA, and we define a measure on calligraphic A. So a set function mu defined from calligraphic A into the closed interval 0 infinity is called a measure if it satisfies the following condition. So first condition is that mu of the empty set is 0. It's a bit similar. This is similar to the first condition that if you recall the definition of an outer measure, we also have this imposition that mu star of the empty set is 0. So for a measure, we also need the condition that mu of the empty set is 0. And for any A, mu A should be in the interval 0 infinity. Actually, by definition, we already implied it here, but it's also good to mention that in the definition because there's something you need to prove. And finally, the last axiom that mu should satisfy to be called a measure is that it should be countably additive. To say that mu is countably additive, it means that if you take a sequence of pairwise disjoint sets, AK, of course, subset of capital X, mu of the countable union of AK is equal to the series of mu AKs. So if we have a measure over A, the triplet XA and the measure itself will be called a measure space. If you recall, when we introduced the concept of Lebesgue theory, we saw that the function under the integral sign should be measurable, right? We mentioned measurability. And we are going to define what it means for a function to be measurable. So we assume that we have two measurable spaces. That is, the first one is X, the couple X or the pair X calligraphic A, and the pair Y calligraphic F. And we define a function f from capital X to capital Y. So such a function is measurable or A measurable if it satisfies the following property. For any A in calligraphic F, the preimage of A is in calligraphic A. So A actually, as we can see here, is a sigma algebra on X, and F, calligraphic F is a sigma algebra on Y, and calligraphic A is a sigma algebra on X. So those are the two sigma algebra that we use to define a measurable function. So in other words, a function is measurable if the preimage of measurable subset of Y is a measurable subset of X. So in particular, if we take Y to be equal to R, the set of real numbers, and if we take F to be B, and B is what is the Borel sigma algebra, right? Borel sigma algebra of R. then f is measurable if and only if the set of the form, if the set of x such that f of x is greater than a is measurable or is a measurable, and this should be true for any a in R. So why can we take this? Because remember, my battery is running low. I need to quickly, okay, great. A moment. I think here we'll take a pause and continue after, because this introduction is a bit long. I'm going to stop here so that the video will not be too heavy or too long.